In the previous few slides, we have already discussed what is the effect of pole location in S-plane to the behavior of the system. The behavior can be stable, unstable, or marginally stable. In this topic now, I will share to you how to define the stability of the system in a simpler way, in faster way. This section is called as a Routh-Hurwitz. I will explain it to you what Routh-Hurwitz is. So we have already completed the discussion on stability and relating the pole's location to the system behavior. Now we are moving to the next bit to Routh stability analysis. We have discussed this pole location map in the previous few slides. So as what we have already discussed, this map will tell us how the system will behave for different location of the pole. But if you need to analyze whether your system is stable, unstable, or marginally stable based on this pole location map, you need to identify first the poles. You need to know where the pole locations are. And how to find the poles? Of course, you need to factorize the denominator of the transfer function, or you need to find the roots of the characteristic equation. You might be able to do that, but sometimes it's not easy to factorize it. It's not easy to find roots of a characteristic equation. Stability of a linear closed loop system, as I have already mentioned, is based on the location of the poles. And we have already discussed this before. For system to be unstable, you just need one pole in the right hand plane. So one single pole in the right hand plane, either it is complex or real, is enough to make your system unstable. If you want to have stable system, all of the poles in your system, if you have more than one pole in your system, all of them have to be on the left hand plane. If it is real, then you need to have a negative real pole. If it is complex, then the real part of your poles should be negative. So all of the poles should be in the left hand plane if you want to have a stable system. If I can recall again one of the slides that we discussed in the first week about final value theorem, I literally mentioned last time that final value of a function exists only if all poles of your function ft in Laplace domain, it is fs, lie in the left half of S plane, or saying lie in the left hand plane of the S plane. So that is what I meant by saying all of the poles of your fs should have negative real part. So that's how we relate the theory of this final value to the pole location that we have discussed. Okay, let's go back to the story about stability now. Stability is a property of a system. It's independent to the input. So you can have a system that is going to infinity, but the system is still stable. How can it be? For instance, if you give infinite input and then your system is stable, of course, the response will go also to infinity. But the system is still stable, even though the response is going to infinity. Why? Because your input is also driving the system to infinity. So if you want to see whether the system is stable or not, you have to give a constant input. You have to give a bounded input. You have to give an input that is enclosed within a certain value. And then from there, if the response is going to infinity, then your system is unstable. If your system is converging to one specific value, then your system is stable. So stability, again, here I need to stress here, is the property of the system. You cannot see the stability from the response while the input is also going to infinity. So once more, stability is a tag to the system. We have already discussed this many times, how to determine the stability of the system, you just find the poles of the system from the transfer function. How to find the poles? You just solve the characteristic equation. You just find the roots of the characteristic equation, where characteristic equation is equal to denominator equal to 0, right? But sometimes it's not very easy to find the roots of the equation. Well, it might be still easy if you are in front of your computer, but if you are only holding a pen and a paper, it might not be that straightforward to find the stability of the system. Let's take an example first. So let's assume we have a system where the characteristic equation of the system looks like this: s squared plus 4s plus 3 equal to 0. That means the denominator of the transfer function of your system is equal to s squared plus 4s plus 3. How to identify the poles? You just find the roots of this characteristic equation. If you find the roots, you just simply factorize the left hand side. You will get s plus 1 times s plus 3 equals 0. So you can find it easily that the poles are at -1 and -3. All of them are negative. That means all of them are in the left hand plane. Your system is stable. Second example, you have a system where the characteristic equation is equal to s squared plus 2s minus 3 equal to 0. Find the roots. You have a roots at +1 and -3. One of the poles is positive on the right hand plane. Your system is unstable. Just as simply as that. Now let's take this case. You have again another system, but the characteristic equation of your system involves a higher order polynomial of s. In this case, you have sixth order of polynomial of s. You don't have computer in front of you. How are you going to determine the stability? We cannot easily factorize this sixth order polynomial easily. So how are we going to determine the stability without factorizing the characteristic equation? There are a few methods for this. Routh-Hurwitz is one of them, and the other one is Routh-Locus. In this particular topic, I will discuss Routh-Hurwitz method. Routh-Locus will be covered in another lecture when you are discussing about controller design. So we will focus on the first one now, Routh-Hurwitz method. Let's take a case again here, a general case of a dynamic system where the transfer function of the system looks like this, right? We discussed this many times also. So in this case, then you will have n number of poles and you will have m number of zeros, right? Based on the order of the denominator and the numerator there. Before we discuss about Routh stability criterion, I will share you what we call as a necessary condition of a stable system. I will share you a necessary condition but not sufficient condition of a stable system. What does it mean? Let's consider a stable system. If the system is stable, the coefficient of the denominator, which are a naught, a1, an minus 1 until an, all of the coefficient of the denominator should have the same sign. So if it is positive, all of them have to be positive. If one of them is negative, all of them have to be negative. This is one of the necessary condition of a stable system. And the second condition is that none of the coefficient missing, which means none of the coefficient is equal to 0. Okay, so again, this is the necessary condition. Why do I call it necessary condition? This is a necessary condition because if your system is stable, your system will hold these two conditions. But it doesn't mean that if these conditions are fulfilled, your system is stable. Okay, so again, if the system is stable, these two conditions are fulfilled, but it doesn't mean that if these two conditions are fulfilled, your system is stable. You cannot say that. So let's take an example again here. I have a system where the characteristic equation of my system looks like this: s squared plus 4s minus 3 equal to 0, saying that the denominator of the transfer function is equal to s squared plus 4s minus 3. What do you see here? The first term, the coefficient is positive 1. The second term, the coefficient is positive 4. The third term, the last term, the coefficient is negative. So not all of the coefficient have the same sign. This doesn't fulfill the condition. So in this case, you can say that the system is not stable. I said not stable here. It can be unstable. It can also be marginally stable. Let's take the second case. If you look at the characteristic equation, I have s power of 6 plus 7 s power of 5 plus 9 s cubed plus 8 s squared plus 3 equal to 0. One of the coefficient is missing, isn't it? The coefficient of s power of 4 is equal to 0 here. So this is your system in this case is also not stable. Again, it can be unstable, but it can also be marginally stable. So again, I want to stress it again here about the necessary condition. If all of the condition in the previous slide are met, the two conditions that I mentioned, you cannot conclude anything because of that necessary condition. If the system is stable, the two conditions are met. But if all of the conditions are met, it doesn't mean that the system is stable. That means you cannot conclude anything. It can be stable, it can be marginally stable, it can be unstable as well. Again, in other words, then I can say if all coefficient on the characteristic equation are of the same sign, this the first condition, and none of the coefficient is 0, the second condition, it doesn't guarantee the stability. You cannot conclude anything. The system again can be stable, unstable, or marginally stable. So how do we know if the system is stable and unstable or marginally stable in a case where the two conditions are met? In that case, you have to apply Routh-Hurwitz technique. What is Routh-Hurwitz? Routh-Hurwitz, using Routh-Hurwitz, you can identify the stability of the system without a need of factorizing the denominator of your transfer function, without a need to solve the roots of the characteristic equation. How to do that? You need to form what we call as Routh array. So what is Routh arrays? This is a simple illustration of Routh array. So let's say for a general case, we have a dynamic system where the characteristic equation looks like this. So in this case, your system is a nth order system because the denominator has a highest order of n. This means, of course, you will have n polynomial. Imagine if n is very large, you cannot factorize the characteristic equation. So how to identify the stability of the system? You have to form the Routh array. So how to do that? First, you have to list all of the power of s from the highest one, Sn, Sn minus 1, Sn minus 2, all the way until the last one, S0. S0 means the last monomial of your polynomial of S, which is a constant basically. And then after that, you can start to assign all of the coefficient on the array. How to do that? Let's start it from the coefficient of s power of n. I put it here, just next to the s power of n. And then a1 is coming from s power of n minus 1. And then next is a2, but be careful here. A2, I will not put it here. You don't put it here, but A2 you will put it there. Same to A3, A4, A5 until the last one AN. So you have to put it alternately between the first two rows. Okay, so the first two rows are derived from the characteristic equation. And then what next? You have to calculate the remaining elements from the third row below. So all of these numbers, B1, B2, B3, all the way until Bn, all of them are the numbers that you have to calculate it with a certain formula. Let's take an example of a system where the characteristic equation has a highest polynomial order of 5. So in that case, then when we are constructing the routes array, we start from S5, S4, S3 all the way until S 0. And then I put all of the coefficients from the characteristic equation A 0, A1, and then the second one, A2, I put it here. Be careful with that. A3, A4, A5. Those are the numbers that we found from the characteristic equation. And then next, you have to compute B1, B2, B3, C1, C2, and so on. So how to calculate all of these numbers, I will share it to you in the next slide. B1, B2, everything, C1, C2, all of them are computed using this formula. So if you know these formulas, you can complete the route array, and then eventually you can conclude the stability of the system. The question must be, how can we memorize all of these formulas? These formulas look complicated in a sense, but luckily there is a nice patterns from this formula. Let's construct again the routes array for a generic problem. So again, as I mentioned, the first two rows are derived from the characteristic equation. And then the remaining rows starting from row 3 below, you compute it using the formulas. Now, how to find B1? You have to use this formula, but there is a nice pattern. So you don't have to memorize the formula, you just look at the pattern. How to do that? You are going to compute B1. Just look at the two rows and two first column above it. So look at these two columns. And then assume this as a 2 by 2 matrix. 2 by 2 matrix where the elements are A0, A2, A1, and A3. And then to compute B1, B1 basically is the negative determinant of that matrix divided by the last element on the first column. So this will be the result. So B1 basically is the negative determinant of A0, A2, A1, A3 divided by the last element on the first column, which is A1. Now, what about B2? For B2, we do the same thing, but you have to retain the first column, A0 and A1. And for the second column, you take the next column after B2. So we are going to calculate B2. You have to take a look on this matrix of A0, A1, A4, and A5. So when you are going to compute B2, B2 basically now is again the negative determinant of A0, A4, A1, A5 divided by same thing, the last element of the first column, which is A1. Okay, so there is a nice pattern there. You do it again for B3 if you have to refer to the matrix of A naught, A6, A1, A7, and so on and so forth. Right? Do this until you complete a third row, the s power of n minus 2 row, until the value is becoming 0 and it always zeros. That means you complete the third row. Now we move to the next row, the fourth row. How to compute C1? Same thing like before. You look at the two rows above the row of C1. And then we do the same thing. You consider this 2 by 2 matrix, A1, A3, B1, B2. So this will be C1 will be equal to the negative determinant of A1, A3, B1, B2 divided by the last element of the first column, which is B1. And then after that, C2, you do the same thing. For C2, we take a look on this 2 by 2 matrix, A1, A5, B1, B3. C2, then it will be negative determinant of that matrix divided by the last element on the first column, which is B1. You do this until you complete the third row. If you still have a fourth row, fifth row, and until the last row, you have to complete all of them. And then after you complete all of the rows, you are ready to conclude the stability of the system. So how to conclude the stability of the system? Once you complete the routes array, you just have to take a look on the first column. The first column of the route array. If there is no sign change on all of the values on the first column, then your system is stable. So if A naught, A1, B1, C1, all of them are positive or all of them are negative, then your system is stable. If there is a sign change, your system is unstable. It must be unstable. You cannot have marginally stable. It must be unstable. And how many times the sign change on the first column will tell you how many poles in the right hand plane. So that's how to conclude the stability of the system using Routh-Hurwitz technique. Let's take this example now. I have a system where the characteristic equation, you can see it in the slide. The characteristic equation is equal to s power of 4 plus 4s cubed plus 9s squared plus 10s plus 4 equal to 0. I want to determine the stability of the system. So I form the Routh array starting from S4, S3, S2, S1, S0. And then I put all of the coefficient of S4 is 1. And then 4, I put it here, 9, 10, and 4, the last one. So I complete the first two arrays. And then I can start to compute the remaining rows. B1, you can again compute it as follows. You look at this matrix and how to calculate B1 is negative determinant of that matrix. 4 times 9 minus 1 times 10 divided by the last element of the first column, which is 4. It's equal to 26 over 4. B2, I take a look on the matrix with this element 1, 4, 4, 0. So the negative determinant will be 4 times 4 minus 1 times 0 divided by 4, the last element on the first column. This will be equal to 4. I don't have to calculate the remaining numbers on this row because all the way here B3, B4, all of them will be equal to 0. So I can move to the next row. For C1, I just have to take a look on this matrix 4, 10, 26 over 4, and 4. And then if you calculate it, C1 is becoming 7.54. I don't have to compute again the next column because it definitely will be equal to 0. I can move to the next row. Same thing again for next row D1. I have to take a look on this matrix divided by, I calculate the negative determinant of this matrix divided by the last element of the first column, 7.54, and then I will get D1. D1. D1 is, will be equal to 4. We have our routes array completed now. We can conclude the stability of the system. Just simply look at the first column. What do we see here? 1, 4, 26 over 4, 7.54, and 4. All of them have the same sign. So your system is stable. You can check it if you have a computer with you, if you have a good calculator with you, which can factorize a higher order polynomial. After I use my own computer, I can factorize the denominator here. After I factorize it, it is becoming like this. And then I can factorize it further. From here, I can identify the poles of this system. If you see, after I factorize it, I will have twin poles, twin real poles at -1. And then I have a complex conjugate pair of poles where the real part are -1. So from here, all of the poles are in the left-hand plane. The system is indeed stable. So using this Routh-Hurwitz technique, you don't have to factorize it if you want to check the stability of the system. But of course, you cannot identify the poles. At least you know if the system is stable or not.